Hello there, and welcome to this video on the use of cross-validation and linear classification of EEG data. I'll start off with a brief overview of what happens in a world without cross-validation, which hopefully elucidates why we should use cross-validation, and then I'll go on to describe several different approaches that can be used for cross-validation. So, yes, I'll start off this lecture by talking about circularity. Circularity is a trap that is easy to fall into no matter what kind of research you're doing. If you're doing some kind of statistics, then there's the potential for circularity. A working definition we can use for circularity here can be a series of analytical steps where the data are first analysed to select a subset, and then that subset is reanalyzed to obtain results. In other words, we take a look at the data set, we see where we can observe the effect that fits our hypotheses, and then we select the parameters to best draw out this effect. Circularity arises because there is a statistical dependency between the data we examine and the data we analyze. So, for example, we may look at a topography and see that the effect is most prominent over occipital electrodes. So, we then go on to restrict our statistical analyses to these electrodes. Or we can do this in a temporal sense. We could say we see that there's an ERP most prominent at around 300 milliseconds. So we epoch our data in such a way that we exclude time points which are not close to this 300 millisecond marker. Now, whenever we do this, we overinflate the size of our effects. We can say, wow, this is amazing, this effect is huge, but in actual fact, we may be looking at an incredibly small effect, both statistically and in real descriptive terms. But our analysis pipeline has just led us to believe that these results are incredible. So this is circularity, and it's a big problem for classifiers in EEG. Classifiers such as LDA literally take a look at the data, they describe how best to find your effect, and then apply those weights to separate the data out into two conditions. And this is the very definition of circularity. So how do we resolve this issue? Well, circularity arises when we use the data to inform our analysis pipeline of this very same data. But if we look at the data that is statistically independent from this first data set, then the issue of circularity goes away. And we can achieve this by splitting the data into what's called training and testing data sets. These data sets are independent of one another, so the use of one data set to inform analyses from a second data set avoids the issue of circularity entirely. So just before I move on, a quick disclaimer. I've said that it's circular to select channels or time points or whatever's based on how the data looks, but it's important to note that if you select these channels or time points a priori, that is, if you've created a hypothesis before you collect the data, which says you're going to look for the data at this channel or at this time point, then circularity isn't an issue. It isn't an issue because you've defined these hypotheses before you've looked at the data, and yes, they've been defined on hypotheses, so there cannot be a statistical dependency based on how you've analysed the data. This is also a major benefit of pre-registration and registered reports. You can pre-specify and record your hypotheses, and then when people can later see these regions of interest you've chosen, you can demonstrate that it was not driven by the data, but it was a hypothesis and then not subject to circularity. So how do we address circularity? Well, this is where cross-validation comes in. In a nutshell, cross-validation is a process of applying an analysis approach driven by the analysis of one data set to a second independent data set. If the analysis pipeline, if those weights derived from the first data set can be successfully applied to the second data set, then we can infer that these weights derived from the first data set carry meaningful information about the content of the EEG signal we're analyzing. In more concrete terms, imagine we have an EEG data set in which participants are shown blue or yellow stimuli. We could therefore apply linear discriminant analyses to this data set to see whether the EEG carries any information about the stimulus categories. If we just train our classifier on the entire data set and then apply these weights to the same data set, then we have the issue of circularity discussed on the last slide. If, however, we train our classifier on a subset of the EEG dataset and then apply the weights to a second independent subset of the data, then there is no issue of circularity. Critically, if we apply these weights to a second independent subset of the data and we can continue to discriminate between the two stimulus categories, then we can infer that the EEG signal contains information relevant to the identity of the stimulus. So that's cross-validation, really. That's applying the weights from one data set to a second independent data set and seeing if we can still decode the data. So, well, how do we do this? First, we need to prepare our data. And then we need to think of a way which is suitable to cross-validate our analyses. Third, we need to partition the data into subsets that are appropriate based on this cross-validation approach. And fourth, we need to train the classifier on a subset of this data before applying it to the test data set. Okay, so I'm going to start talking off by talking about preparing the data. So before we start cross-validating our analyses, we need to make sure the data is prepared in a sensible, straightforward manner. On the right, in this little diagram we've got going on here, we can see a very simple analysis pipeline. We start off by reading the data, then filtering to get rid of line noise artifacts, epoching it around our stimuli. Perhaps if there's lots of channels and we just want to reduce those features a little bit, we do a bit of feature reduction, such as PCA. And then we get onto these blue boxes here, and this is where we need to start considering cross-validation. So first, it's when we come to partition the data. So how do we split the training and test data sets? Then we go on to training the data on one of these partitions, and then we apply to the test data. So in previous videos, these various pre-processing techniques have already been discussed. So I'm not going to repeat what's already been said, but I will say this. It's incredibly important to make sure all the data goes under the very same pre-processing steps. Take, for example, the case where you have two conditions, the perception of blue stimulus, the perception of the yellow stimulus. If you have apply heavy filtering to one condition and not to the other, then the classifier is going to leap on this difference. If you put a very high or a very heavy low pass filter on the data for the blue stimuli but not the yellow stimuli, the classifier is going to go, hey, there's a lot of high frequency activity in the yellow stimuli which is not present in the blue stimuli, so let's use that to classify our data. And this same idea applies to feature reduction as well. If you use principal components to reduce the dimensionality of your data, but use different weightings for the two conditions. So in other words, that is, you apply PCA to the two conditions separately, then you'll introduce artificial differences into the data set, which they'll give you amazing results, but they're useless, they're meaningless. So when it comes to cross-validation, you need to be sure that you're running cross-validation on identical data sets. Okay, so that little disclaimer out of the way, I'll go on to the first method for cross-validation. And this is called the leave one out cross-validation method. So in the leave one out approach, you split your data into two data sets. A training data set consisting of all the data points apart from a single data point that you're going to exclude as your testing data set. So if we take this big data set here, we've got some trials where they've been shown a blue stimulus, trials where they've been shown a yellow stimulus. And if we're going to do the leave one out, then we take all the trials, this very first one, and include that in the training data set where we train our LDA, we get those weights we want to use. And then later on, we apply these weights to a single blue stimulus, which was shown first. And then we test and see how generalizable it is. Do these weights from this first training set apply to the test data set? If they do, great, we've got a generalizable classifier. But we also need to repeat this process on and on. So then we take the second trial, we take that as the test data point and use the rest as the training data set. We keep going on, so we do the third trial, the fourth trial, all the way up to the very last trial. And we recompute how well our classifier has generalized the test data set. So this is a really effective cross-validation approach when you only have a small number of trials, because it ensures you've got a very big testing data set. And yes, it provides the largest possible testing data set you can have. However, that is also its limitation. But because you have to essentially go through every single combination of trials, or you have to run this training and then testing on every individual trial, then it's very computationally intensive. And sometimes if you have a lot of trials, if you have 300 trials and you need to train and test 300 times on an individual time point, then it's going to take a very long time to do. So you really need to kind of have a bit of a think about what's important here. It's by far going to give you the best training data set, but it's also going to take a very long time to compute. So an alternative approach, which is less computationally intensive, is what we call k-fold cross-validation. So yes, let's consider a case where we've got huge amounts of trials. So we've got 200, 300 trials. We really don't want to use the leave one out procedure because it's going to take forever. And truth be told, there's a law of diminishing returns on massive training data sets. If you added a couple of extra trials to a really small training data set, then those couple of extra trials might really help improve the fitting of the weights to the training data set. But if you add a couple of extra trials to the data set, which already has 200 trials, then it's going to make very little difference at all. So in these cases where we've got a lot of trials, then we can look at k-fold cross-validation. So k-fold cross-validation involves splitting the data set into k-folds or partitions, where k is a number you have to decide on, which pretty much tells you how many times you're splitting the data. In the example we've got in this figure here, we've taken the data set and we split it into 2 folds. So this would be a 2-fold cross-validation, so k equals 2. Here we can begin by using the first fold as the training data set, and we can apply the weights to the testing data set, which is fold 2. We can then repeat the process by flipping it around so that we train on fold 2 and apply to fold 1. And we can see how well the data set, how well the weights generalize to the testing data set. And you can also just see this lovely little cross as maybe a hint of why we're calling it cross-validation. We're literally swapping out the data sets, switching them around to see which way best fits the data. So this approach is much more efficient than the leave one out approach, as you only need to train and test the data k times. But there are a lot more free parameters using this approach, so you have to decide how many folds you're going to use. You're going to decide how best to separate, how best to fold your data, how to define those partitions. Now, all of these parameters, there's going to be a separate video on, so I'm not going to jump into it here, but you need to consider the fact that with so many free parameters, there's always the possibility that you might accidentally exploit these researcher degrees of freedom and find the way which the classifier best works for you based on whatever parameters you found work best, and then it gives you a great result. But ultimately, because you've been searching for those best parameters, the result again is somewhat circular, it's somewhat overfitted, and really has very little generalizable meaning to another data set way to bring it in. Okay, so now we're going to go on to a separate approach which requires a different sort of experimental design, and this is called the sort of localizer or holdout approach. So sometimes you don't necessarily want to train and test on the very same data. Sometimes you might want to see if these neural representations you're looking for are able to generalize to other contexts. For example, in memory studies, we can ask whether a neural representation of your stimulus processed during encoding is similar to how it's recalled, that's retrieved stimulus representation. In these cases, you might want to use a localizer or sort of a cross-decoding approach. So a localizer we can think of as a separate block of the experiment in which participants are presented with the stimulus of interest, but they're not really engaging with them, or they're not engaging with them in the same manner that they are during that epoch we're really interested in. So yeah, this would tell us how the training data set looks like when the stimuluses are simply being perceived. And then we can take these weights and we can apply them to a different task, such as how the stimuli look when they're being retrieved rather than just perceived. And we can see if these weights decode neural representations of the recalled stimuli. Now, this approach will be the fastest validation approach because there's not really any cross-validation going on at all. You really do take your localizer using it as the training data set, you take your test data, and that becomes a test data set. You don't really need to flip this around because you're not interested in that question. So it is going to be the fastest approach. Also, because the two data sets are completely different tasks, the likelihood of circularity or some weird effect of popping up because of experimental overlap is really reduced, which is also really nice. However, it does assume that those representations generalize across conditions. So again, we go back to the memory task, then it assumes that those neural representations of stimuli when you're just passively viewing them are the same in their representation as what they are when they're being recalled. And this is not always the case. It can be an interesting question in its own right, but yes, it can also be the case that these just don't generalize across from a localizer to a test data set. So then I'm going to give you one last cross-validation approach, and this is perhaps the most hardcore approach, and this is the lockbox method. So this is essentially a sort of cross-validation within a cross-validation. So you would start out by separating the data and placing it into one subset. So, well, yes, let's say we split the data into 3 folds. We've got 1, 2, and 3. What we do is we take 2 of these folds, we put this into our analysis pipeline, and we take this 3rd fold and we put it in the lockbox, which we never touch, we never play with. And with this remaining data we've got, then we can just go nuts. We can really just train, test, repeat the process, see which way is best to separate out all these data, best to cross-validate, and then just find those optimal parameters on fold 1 and fold 2. But it's important to remember you just do not touch fold 3. So because you haven't touched fold 3 at all, whatever you've done here, as long as it generalizes to fold 3, so you found the optimal parameters, you spent ages just kind of fine-tuning it, tweaking it to see what parameters, what folding works best here. Once you found the weights which work best here, you can then apply them to fold 3. And then if it generalizes to fold 3, which you've never been playing with at all, then perfect. It will tell you that these do generalize, these weights do generalize to independent data. And because you haven't been repeatedly testing and training on the 3rd fold, then there's no issue of circularity. So this is definitely the most hardcore approach, that if you just keep this whole data set from the moment you record it and never look at it till you've completed your pipeline, you've completely determined it, then you can't be concerned about circularity, because if the data is circular, if you found those parameters which just sort of overfit to this data set, then they should never fit to the fold 3 data set. Now, of course, it does have this drawback in its own way. There's definitely like it's very time consuming essentially, but if you're going to keep trying to train and test and see which best way to fold the data, best way to partition your data on here, then it just requires a lot of tinkering and takes a lot of time. So that's always something to kind of factor into when you're designing its analysis. But I would say it's also, so long as you do it properly and you never touch this data up until the point of your very final analyses, once you've decided on the weights based on this individual, this separate analyses, but it's perhaps the most secure approach there, which, yes, provides optimal conditions for data exploration. So, the best way to measure an effect without introducing circularity into the analysis. So, which method should you choose? Which I think is a good question to ask. Well, unfortunately, there's not really a gold standard, and each approach has its strengths and weaknesses based on the data set. The leave one out approach provides most extensive training data set. but it also comes at the cost of computational time, and with large data sets, it may just not be feasible to execute. The localizer and k-fold approaches are much faster, but they also make more assumptions about the data, such as how best to fold the data, how best to partition, how many folds, how many partitions. All of this, they all kind of become assumptions for free parameters for the analysis. Lastly, the lockbox is maybe the most statistically safe approach, as you can tinker around with what are the best ways to fold the data, what are the best ways to partition the data, and then you can't apply it to a completely independent data set which you haven't been tinkering with. However, this takes much more time and it's much more personally intensive to implement. So the decision really is yours to make. In the next tutorial, I'm going to give you a little idea of how we can choose these approaches, how these different approaches influence the data analyses, the effects, and then hopefully, as we go through more of that, it becomes clear, or maybe in your mind, you get a better idea of which approach you think is best used. So that's it for this little video. I'll give you two papers I'd really recommend reading. So first is one by Krieger-Skorda and colleagues. So they had this paper back in Nature Neuroscience in 2009, and it really nicely describes the issue of circularity and really why we should be cross-validating the data. It's a really nice, well-written paper, it's a good read. And then there's a second one, which is really about the lockbox method by Powell and colleagues, called I Tried a Bunch of Things, and how these sort of free parameters can, or these research degrees of freedom can lead to overfitting when you classify them, and it highlights how best to do this lockbox method. So I'd recommend giving those two a little bit of a shot if you want to learn a little bit more about cross-validation and circularity. But for now, thanks for tuning in, and speak to you again.